Okay, well, welcome everybody. It's my pleasure today to introduce as our Data for Good speaker, Chris Kenyon. Chris is Global Head of Quant Innovation at MUFG, where he is also Global Head of XVA Quant Modeling. Chris has held several prominent quant positions in the financial industry, while also managing to publish extensively, particularly in the area of counterparty credit risk, and while also holding a faculty affiliation in mathematics at University College London. Most recently, Chris has been studying the implications of climate change for the financial industry, and we're very pleased that he's agreed to join us today to share his work. So Chris, over to you.
Okay, so thanks very much for the introduction. And can I just check that you can see my slides, my screen?
Yes, very, very well.
Okay, so today I'm going to look at a transparency principle in order to kind of push towards sustainable finance. And the key word is transparency, because it's not changing anything that already exists. It's simply revealing what is already known and then following through on the financial implications. So the usual acknowledgements and disclaimer. I'm first going to talk a bit about the context and then the carbon equivalence principle in more detail. I'm going to look at the methods, and what you find looking at this is that you have to develop new sets of methods in order to tackle different aspects of the problem. And then I'm going to apply the carbon equivalence principle to project finance. So I've picked power generation, but you could pick any other project finance case where emissions are involved, and then draw some conclusions. So the key question is incentive alignment, because talking about default, if you think of the planet as a counterparty, in that case, sort of planetary default is kind of the worst counterparty default you can come across. So this is a significant interest. And also many banks have declared that they will have carbon net zero by 2050, and that includes the bank that I work for. So what we're after is incentive alignment. And what we demonstrate and claim is that giving carbon equivalent emissions the same status as cash flows can provide this alignment. And what this principle kind of pushes us towards is financial net zero rather than carbon net zero, on the basis that carbon net zero is expensive. And what we're after is something that is, ideally financially zero. So our target is financial net zero. And of course, that means net negative carbon emissions. There are a lot of starting initiatives about carbon prices and taxes. There's a good review that the World Bank publishes every year, and I've included a reference to that. And they list about 66 different initiatives. At the moment, they are mostly non-material, because relative to world GDP, it's about 1 basis point. So 1 over 10,000 in terms of the cash flows involved. In some jurisdictions, it's a lot more, but this should be looked at as something that is developing rather than already in existence. And this has implications for project design, as we'll show. So one of the ideas of the carbon equivalence principle is you simply have 2 term sheets. One is for cash, and the other is for the carbon equivalent effects. So that gives you a new currency, which we've called XCE. Now, by carbon effects, we want to capture the carbon flows that the financial product enables or causes. So enable would be you're financing a power plant. Your causing would be how much carbon does it take to keep the financial product that you're dealing with in play. So there's been a number of analysis of Bitcoin, and high frequency trading is another area. So if all the power, all the electricity is coming from renewables, that's fine. But then you have to say, then you have to check that that's what's really happening. Now, roughly 40% of the world's banks have signed up to the net zero partnership by 2050. So this means that the bank's loan books has to get down to net zero carbon in 28 years. And if you think of the length of a loan, which might be 10 or 20 years, that means we've already started. So it might sound silly, but a basic requirement of getting to zero is the ability to do arithmetic. So if you think about green bonds, green is a binary label, so you can't do arithmetic. So that's not sufficient to permit the banks to get to net zero carbon emissions equivalent. So what we're going to end up with is showing that given the potential risk of and costs of carbon emissions, going for net zero or carbon net zero is simply good risk management. And if you want good financial management, then you want to take the next step and aim at financial net zero. So the idea is to have the carbon flows to have equal status. So that means that you basically have carbon term sheets. So this kind of improves upon other disclosure ideas, because what we're saying is that the carbon flows should be consistent or compatible with existing position keeping systems, because once you've got it in your position keeping system, then you can apply all the usual pricing and risk management to the carbon flows just the same way you do with the equivalent cash flows.
Chris, can I ask a question?
Yeah, please do.
I'm just wondering if this sort of structure doesn't potentially encourage the creation of vehicles just to create opacity. So you have some sort of entity that gets created between the bank and the power plant that gets created just for the purpose of sort of obscuring exactly what you're trying to measure here.
So that would be, can we create some special purpose vehicle that we lend money to and they don't tell us what they're doing with the money?
Right.
This would violate the basic principle of know your customer. And if you're lending, like in a syndicate, something like 2.5 billion for a power plant, you definitely want to know your customer.
Okay.
So
thanks.
In terms of financial products, we're talking, 40% of the world's banks. So that's a huge cash flow. And the credit department really does know where the money goes.
Thanks.
Because, we want it back.
Right.
Okay, so this is a quick overview of the problems that come up. So first off is, how do you get a price or a cost, and how do you assess the risk? And then, how is it going to affect the recovery rate? Because project finance traditionally and historically has very high recovery rates, because once you've built the thing, it's basically going to work. Well, that assumption actually needs revisiting. And then there's negative carbon or carbon sequestration. And the question is, you've captured some carbon. How long do you capture it for? Because to be useful on a climate timescale, the basic assumption is that you capture carbon for 100 years. So doing it for 5 years is not really going to help us between now and 2050, or even by the end of the century. So there are some long horizon problems that we need to deal with. And then, as I mentioned, we're looking at financial net zero. So this means combining regulatory and voluntary carbon markets. So some of this is starting to exist. For example, there are various commercial entities which will now provide you with sort of instruments with which to trade some of the voluntary markets. So it's starting to exist. So what are the contributions of this paper? So firstly, to introduce the principle. And part of the principle is removing the label green and demonstrating that most financial products are already ESG related. So that's environmental, social, and governance. Secondly, we provide a set of quantitative methods for dealing with these problems, and also show that there's a whole lot of problems that we haven't solved or that could be solved at a deeper level. And as I've mentioned, 40% of the bank assets of the world are part of this net zero banking alliance for net zero emissions by 2050. And, if you think about financial products that are traded, if you think about, for people who have a mortgage, think about the length of your mortgage. Is that longer than 28 years or shorter? Okay, so let's look at the principle. So there's 3 parts. The first part is, what is the scope? So the idea is that the carbon equivalent emissions and sequestration enabled and caused by a financial product shall be linked to the financial products. So caused means if the financial product wasn't there, they wouldn't happen. Second one is how that the carbon equivalent emissions and sequestration shall be represented as term sheets the way we do it for, dollars, gold, oil. From the point of view of position keeping system, carbon is just another item in the configuration. So there are differences, yes, because you don't actually have a contract for delivery of carbon to the atmosphere or the opposite, but it's still a very good system for keeping track of everything. And in practical terms, what you would do is basically book 2 trades, and in a particular system that I'm familiar with, simply set up a strategy ID to link the 2 trades. And then, everything that's already available is still available in terms of pricing and risk management. And then, as mentioned, the green label is simply inadequate. It doesn't allow you to do arithmetic, which is kind of a very basic requirement. Okay, so now let's talk about the implications. So inasmuch as any financial product causes or enables carbon flows, then it's linked to climate change. So you don't need to add a special extra term to get an ESG financial product. The financial products you have are already doing that. Okay, And second one is product maturity. If you need permanence or permanent sequestration of carbon for 100 years, then you've got to start really thinking about life cycles of different parts of the project. Obviously, the next one is price discovery. So at the moment, price discovery is terrible. Liquid markets go out about a year. You can do various interesting constructs to make that a bit longer, but in terms of tradable futures contracts, that's about it. Now, clearly, there's a lot of interest from market players to make the future prices visible because, you know, we actually have the problem of the loans and the derivatives already. And then the next point, which is once we have the carbon flows in our position keeping systems, then, you know, we can apply everything that we apply to standard cash flows to them. So we can have informed decisions about warehousing, mitigation, you know, risk transfer or carbon risk transfer. So all of this flows from transparency and how we are doing the transparency, which is use the systems that already exist. So just to give a fairly simple example, imagine you have a 20-year fixed rate USD bond financing a coal-fired power plant, or more likely these days, a gas-fired power plant. You have some notional, you pay the notional on one date and you get the notional back on another date, and you have some fixed coupons. Now you need to think about the carbon flows. So first off, you've got carbon from the construction. Then you have carbon from the running cost. And then you've got a bit of extra carbon at the end from the deconstruction and returning the site to whatever was agreed with the site manager at the beginning. So what you'll notice is that this looks completely obvious, that there's, you know, no particular barrier to booking this. Yep, and we'll show the values of some constants later on for a range of technologies. And now I just want to do a short compare and contrast with sort of the green label. So most of the problems with green simply stem from the fact that it's binary. Yes, you are green, or no, you're not green. Whereas what we want in order to get to zero is arithmetic. So, and carbon flows are inherently time dependent. So you need a time dimension as well as a volume dimension. Okay. And then, of course, if you're worried about greenwashing, that, you know, there is significant concern there. And in contrast, if you're just looking at, okay, where is the carbon going? That's a bit easier to track. And of course, you can do all the portfolio stuff once you have the carbon. Notice that I'm talking at a financial product level. I'm not talking about things at a company level. So this talk is focused specifically on financial products. Okay, so let's talk about a few methods. Usual slide with notation, so you can find it later. And we normally start with a probability space of events, a filtration, and a set of probability measures. So here we kind of have the first problem, that we've only got Q, our normal risk neutral measure, out 1 year. And, there's been a fair amount of creativity in specialized carbon prices with jumps using econometric methods and all the rest of it. But, the calibration data just isn't there. And also the market is non-stationary and, very strongly non-stationary because the governments keep changing the rules. So that means that we need to take an alternative approach. And so the standard one in policy making is to use integrated assessment models. So these link an economic model with a climate model. And they've been developed since the 80s. And, they're very widely used. And they're mostly written in algebraic modeling languages. So portfolio type coding languages like AMPL or GAMS. And they're quite widely available. There's quite a lot that you can download if you're interested. And in certain sections of economics, this is really, really well known. So it's a very rich area to pick up price projections and scenarios from. So that's the basic conclusion, that we do scenario pricing, not risk neutral pricing, because the market doesn't exist. Okay. So let's talk about scenario pricing. It's basically dot products of vectors. And the omega gives you the scenario. So for net zero carbon, in this case, we need to pay for the mitigation M on the carbon volume C, and we get discount between now and the carbon flow of capital D sub F for the funding cost, either of the bank or of the project. Notice we haven't said who's paying. We haven't said whether it's the bank or the project, because the first thing we are going to want to do is to see, how big's the number? Is this number comparable with the cost of the project, or 1% of the cost of the project? Because that gives us a scale for how much risk we're talking about. And a convenient scaling is to use an annuity with the maturity of the loan or the financing and the same notional. So that gives us a very natural scaling to understand, how big is the issue that we're looking at. Okay, so now we need to talk about stranded assets. So, as I mentioned, traditionally, if a project like a power station, desalination plant, road, or whatever, toll road, if they default after you've built the asset, what normally happens is you simply extend the loan for a few more years, reduce the coupon, and take a hit. But the thing is there, so you don't really have the chance of losing too much. Historically, according to S&P, on project finance, the recovery rate's something like 75%. So the question is, how much does this additional stress from carbon mitigation affect the default risk? And what we need is some scaling on this annuity spread relative to the CDS spread of the project in order for us to start looking at that. So we can assign that to some function which we can fit in various ways. Okay. The other thing we need to look at is when does the project start paying for carbon mitigation, because maybe it doesn't need to pay anything for 10 years. And then after 10 years, there's some sort of price that it will have to pay. So we can also look at a forward starting spread for what is for the rest of the carbon. So that's quite a useful number to calculate. And then that can give us a scenario and a time-dependent recovery rate, depending upon when the carbon cost kicks in. Okay, so now we can think of a usual ansatz of the CDS spread over loss given default being the hazard rate. And the CDS spread is basically the expected loss. So we kind of have a problem here, because if the recovery rates used to be 75%, then if they move down to 50% for the same project risk, so for the same hazard rate, then we've just doubled the CDS spread, which is the expected loss on the project. So this is kind of a vicious cycle that if the financing spread gets bigger, then the question is whether the project can afford it. And then that can affect the hazard rate as well. So if the hazard rate is increasing and the recovery rate is decreasing, you've got two separate hits on the expected loss. So this is something project finance is particularly susceptible to. So it needs attention. So then you need to say, well, what can we do? So in order for the carbon emissions to end up at zero, then either you can buy an offset permit from, or an emissions permit from the government, if that system exists, or you can look, assuming the voluntary market has now integrated with the regulatory market, you can look at offsets. So you need to include, or think about including, negative emissions technology capacity. And you need to think about building that into the project, because it's a lot cheaper, according to most of the studies, to build it rather than to buy it. Okay, and then we need to say, well, how are we going to make sure that this carbon capture is permanent, where we define permanent as 50 or 100 years? So the cheapest carbon sequestration at the moment, and projected out to 2050, is still planting a forest. So forests default in two ways. First of all, they can simply burn down, in which case the carbon that was captured is released, or the company that owns the forest, that has sold the certificate, the offset certificate, can financially default, and then the assets can simply be picked up by another company, and of course the liabilities are just described by a recovery rate. So we look both at the physical burn rate and the financial default rate, because they can both cause the carbon not to remain captured. And just as a reference point, roughly 1% of US forests burn down every year. Okay, so we can look at, so then this is just back into counterparty credit territory. And we can also look at the rating of the company that is owning the forest. And if that's triple B, then that can be something like 1 or 2% a year. So you can see that the financial default can actually be a bigger problem than the physical default. Although, of course, the physical default is part of the financial default in this case. So what we look at is how much is this going to cost to replace the non-permanent sequestration every so often over this 100-year lifetime. So we can start by assuming that the defaults can be modeled by a non-homogeneous Poisson process with a deterministic hazard rate. And yes, you can make this as complicated as you like, but we were going through for a first analysis, and we can condition on the number of defaults and the probability, and the cost of K defaults. By saying Poisson process, we've kind of assumed that the defaults of the sequestration companies are independent, and we can create an integrated hazard process from the integration of the hazard rate. It's not really a process because it's not stochastic. And then once you have K events within a certain period from a Poisson process, you know that those events are basically independent and distributed on the time interval with a weighting function that is relative to capital lambda and little lambda. Okay, so then we can look at the cost of one default. So that costs us 1 minus recovery. We needs to be discounted back to now, and the replacement costs F of U whenever this is happening. Okay, so then we can put this together and get this more complicated expression at the bottom, but this is still basic probability. And then if we assume a constant hazard rate, we get a lot of simplifications. And this gives us a permanence cost, i.e. how much does it cost to keep carbon sequestrated from now until different horizons. And that's also useful if we want to start at some point in the future and say from that point in the future, we still need 100 years. Okay, so the next thing we're going to look at is financial net zero. So this is build versus buy. So the idea here is simply that the project that is creating the emitting asset builds more negative capacity than it needs and sells the excess capacity on the market. So essentially, we're talking about equation 4. So we're solving for what's the fixed level of capacity that we require, or the overbuild on the negative emissions technology, such that we can afford to pay for all the emissions that we're creating. Okay, so we have some quick methods for addressing each part of the problem. So now let's apply this to an actual case. And we're going to look at power generation. And the US government produces a set of almost engineering specifications across a wide range of technologies every year. And what we're going to do first off is just quantify the spread on the annuity to see what is the scale of the problem we're talking about. And then we're going to follow through on the steps that we mentioned before, looking at the carbon emissions, the potential liability cost of these, and how much negative emissions, i.e. carbon sequestration capacity, that the project would need to build in order to end up at financial net zero. So this is, the bottom line is we can't build the same project that we would have built before considering climate change. Okay, so here's a list of the technologies for power generation. There's actually a few more in the basic documents, but the thing that we're interested in, apart from the cost to build, which is going to be the size, the notional on the loan, is we've got a develop time, a build time, and a lifespan. So if we're talking about 3 to 5 years to develop and build, then by the time the emissions start happening from running, we're 3 to 5 years into the future. So even if there's no carbon pricing now, we have to think about, okay, in 3 to 5 years, is there going to be? And then across the lifespan of the loan, will there be any carbon pricing during that? So in general, the loan will be much shorter than the lifespan of the asset. And so from a purely financial point of view, we're interested in the risks of the loan being repaid. Okay, so this gives the basic setup. So it gives carbon for operation and carbon for construction. And you'll see that the non-combustion technologies like nuclear and wind have zeros on their operating emissions. They would have some, but it's not really relevant at this scale. And then I'll just flip over this, which is the basic setup of where we get all the data from. Just one point about negative emissions technologies. The first or the second column is really the interesting one, which is in what year is this technology expected to be mature? And apart from forests, it's basically 2050. And there's a lot of surveys on this. So the engineering data is, reasonably good. So what we need to do is to say, if we're using this technology earlier than its maturity, then we're going to have to pay a penalty. And there are also some estimates we can find as to how big a penalty we're going to pay for using a technology before maturity. And those penalties are really quite high, something like ×3 to ×6. And we've got a range of estimates for the cost, so we just go for the middle. The carbon price scenarios, we're just taking a set from NGFS. So that's Network for Greening the Financial System. And there's a big database at the URL that I gave. You can also download the models. In terms of financing, we're going to consider 4 lengths, 10, 20, 30, and operational life, always taking the minimum with the operational life. Financial market settings are from US Federal Reserve St. Louis, which has a lot of databases. Yeah, I know I work at a bank, so I've got it all, but this is the public information. One interesting point is BBB discount curve at 5 years versus SOFR. So risk-free rate is about 157 bips. So we use a flat spread for the project. And we did a quick back of the envelope calculation to see, you know, how much carbon are we talking about? So this is the absolutely worst case, which is a coal-fired power plant with no carbon capture and storage. And it's about 4 million tons of carbon a year. So this is why most financial companies don't want to finance coal-fired power plants with no carbon capture and storage, because, you know, if you're talking 4 million tons of carbon a year, and if that starts to be $100 per ton, you're talking, you know, $500 million per year on a capital outlay of $2.5 billion. So the numbers really don't work. Okay, so in terms of cost of technology, first off, there's approach to maturity, and then there's just increase to inflation. The dashed line at the bottom is forest without adjusting for permanence. And then the straight line just above that is with permanence adjustment. Okay. And these are the carbon price scenarios for the US, actually, from this particular model. So there's the delayed transition in blue, which basically says carbon prices are 0 until 2030. There's the green, which is aiming to get to net zero by 2050. And then there's the orange, which is what different governments have already said that they will do. Okay, and what you can see is that planting a forest is most of the time cheaper than what the market price or the market price set by the government is likely to be. Okay, so just some emissions profiles for combustion. So the blue, you know, in most countries, that's simply not going to happen. So it's the lower ones are far more realistic. And then these are the non-combustion. So there's a lot of carbon, potentially really a lot of carbon being used at the beginning for the construction and then a bit at the end. So, okay, so a lot of numbers here. So I'll take let's say the one at the bottom and go through that. So municipal solid waste, landfill gas. What we're looking at is the annuity spread to pay for the carbon emissions according to various scenarios. So the annuity spread for 10 years, if we are going for net zero, so the bottom line, that's 800 bips. And I just said that BBB CDS spread was 157 bips. Now, this is an interest rate annuity spread, so it isn't necessarily comparable to a CDS spread. But in general, the way a loan is priced, it's funding plus risk into the spread. So you're still talking hundreds of bips. So these numbers make most of the combustion technologies questionable, because you can find some that are below 100. But if it's a 20-year loan, they're basically all above 100. So that means some sort of action is going to be needed, i.e. project redesign. If we look at non-combustion, then most of them for a 20-year loan are below 100 bips. For the scenarios that are not, then you need to decide what action is going to be necessary. Now, here I'm looking at the financial net zero capacity. So how much carbon capture capacity is necessary in order to end up at financially net zero. So you can see some NAs in the first column, which means either it's, well, in this case, it's not relevant because this is delayed transition. So it's going, so you basically can't win because there's nowhere to sell the carbon capture to. So there is simply no solution. But for 20-year loans, then if you're talking about sort of gas-fired power plant with 90% carbon capture and storage, then it's about 0.2 megatons per year of carbon capture capacity in order to end up at financial net zero. For non-combustion technologies, most of them are very small. There's a bit more for wind and solar because of, well, there's two reasons. One, because these have a fair amount of initial construction. And also, yeah, that's mostly it. So in terms of a summary on the results, if there's a finance that is required today, then the construction and operation is going to be a few years in the future. So this is kind of a big concern, and especially to do with the objective or the declared objective of carbon net zero. So combustion technologies really look as though they need redesign at the project level, and they need to include persistent carbon sequestration for financial net zero. Non-combustion is much less of an issue, because it's just the construction phase. Let me just, in the interest of time, skip over alternative metrics and just go to the conclusions. So what we've done is introduce the Carbon Equivalence Principle to enable incentive alignment with sustainability. So the idea is provide transparency of carbon flows such that these are compatible with existing bank systems. So it means that we can do arithmetic to get to net zero, and it points out that what we actually want is financial net zero. It also underlines that we don't have to do anything special for most financial products to have a link to the environment. In as much as they have anything to do with emissions, they've already got a link with the environment. And then we applied the principle to a set of project finance and examples for power generation. And there's a significant risk of stranded assets, especially because carbon prices go up over time. They're not going to go down. And so this means that the assumption of very high recovery rates is at risk unless you redesign the project, of course, and add in some negative emissions technologies, which at the moment means forests. And then we have to deal with the fact that the carbon needs to be captured for a long time, maybe 100 years. So what I've basically shown is that transparency to do with carbon flows and the financial risks of these carbon flows has a lot of downstream implications for design, risk, and pricing today. So happy to take questions at this point.
Thank you, Chris. Thank you for a very interesting, thought-provoking presentation. Maybe I'll start off with a question about the financial net zero target. Do you think that's a target that banks will adopt on their own? I mean, why wouldn't a bank take the perspective that if it's able to charge a sufficient spread to compensate for the risk of carbon prices in the future, it's willing to do the loan? What's going to be the motivation for banks to adopt that target?
It's going to be driven by how big is the annuity spread from emissions for the project, if the project is going to have to pay it, because that tells you what stress you're putting on the project. And if you're putting stress on the project, then you're going to have to charge more to the project because the default probability just went up because of the stress. And then if you're charging more to the project because it was under stress, then that is a very vicious circle. So it's, this taking an arm's length approach doesn't really work when you can see that you're causing your investment to have serious risks that it will never come back.
I see. And you're looking at the whole problem very much from a loan perspective, which is natural coming from a banking perspective. But if we think more generally about how these kinds of projects are financed, if funding through loans becomes more expensive, do we end up in a scenario where the same projects just find it cheaper to finance through equity? And how does equity financing of projects factor into this sort of overall framework?
So I would kind of direct your attention back to Modigliani Miller. So that makes the basic assumption that the mix of debt and equity doesn't affect the return of the company. So
but that's on the assumption that there's sort of absent frictions like higher costs. I mean, the kinds of higher costs associated with debt financing here. If debt financing is sort of internalizing the cost of carbon emissions and equity financing isn't, then that might be enough to.
The risk is there. That's the point. Whether it's financed with debt or equity, the stress on the project remains. So you have the same argument from the equity investors. So what is the return on equity that they will require in order to compensate for the risk?
Okay.
And if they start asking too much, then you have the same vicious circle.
We do have one question that just came in. Maybe we can take that. I see From
Okay.
Davide, thank you for the presentation. Congratulations on the extraordinary idea. Have you thought about including a geolocalization point of view on the emissions? I'm thinking in different places, the same amount of emissions would have different effects.
So this gets down to what is the jurisdiction that the emission is happening in? Because, for example, maybe if you're building a power plant in the Netherlands versus a power plant in Australia, you end up in different regulatory regimes. And from an investment point of view, you can think of that as a portfolio problem, which is, where do you have your investments? So I think there is a portfolio aspect, but it's really quite secondary compared to, including the carbon risk in the pricing of the loan.
To the end of the webinar. Chris, thank you so much for sharing your ideas with us. Very interesting perspective. Inspires a lot more thinking on the problem. New interesting new perspective on how to think about the broader issue here. So thank you very much, Chris.
You're welcome. Thanks for the invitation. Goodbye.